much. I'm Adam Johnson, flying in from Seattle late last night. I had some issues getting in here, but I'm really happy to be here. This is such a cool venue, and it's really awesome to see like a really good showing of interest in serverless in Atlanta. So glad that I'm here and that I can share my story with y'all. So I'm the co-founder and CEO of IOPipe, and IOPipe is basically a startup that we started in 2016. And I'm going to give a little background about where we came from, what we do. I'm not going to pitch you on our product. I'd rather talk about like what we built to power our product, which is built on serverless, because I think it's important to share the stories of how people are actually using serverless in production. And we've been early adopters of serverless since 2016. And a little bit of background on us is my co-founder and I came from the infrastructure space. We were in OpenStack for the very beginning of OpenStack. My co-founder was an early employee at Docker. We spent many years deploying large-scale on-prem workloads and clouds for large companies, and witnessed firsthand just like how painful that can be. And when AWS launched Lambda, that was kind of eye-opening for us, and we decided to quit our jobs, start a company, and base it around serverless. So we're like, let's do something in serverless. This is going to be like the next big thing. It's just, very logical that things are headed in this direction. And so we decided to start up. We started in 2016 in the summer. We joined Techstars program in New York City. We're a fully distributed team. My co-founder's in Philly. I'm in Seattle. But we got together in New York, and we had some initial ideas around serverless, and we decided that we needed to validate these ideas before we started building something that doesn't necessarily like solve the right problems. So we talked to we talked to as many production Lambda users as we could find in 2016. There wasn't a ton. There were like 30 that we could find. So there wasn't a lot of people doing production workloads, but we did find people. We interviewed them, and what we really found out was that one of the biggest problems was that there's a big lack of visibility. 29 out of 30 people said almost exactly the same thing. Like, Lambda's great. It's easy to get started. It's easy to push your code out and it just works. But when it doesn't work, then what do? All you have to go off of are some log statements that say it worked or it didn't work, and this is how much you're getting billed. It's not enough to actually know what was going on. And the reason is because a lot of people ended up building kind of mini services instead of microservices. Like Lambda functions, you can choose how big or small they can be. Some people make kind of little monoliths. One of the terms I've heard recently is mini services. So Lambda functions, what we see back then and still today are that a lot of Lambda functions have mini code paths. There's a lot of different state that can flow through those. And if you don't have proper instrumentation or logging around that, you just don't know what happened, right? You just have like millions of log statements that just say it worked or it didn't. And you just don't know what to do. So most of these users we talked to ended up having to build their own instrumentation or spend a ton of time doing logging and then searching through the logs. And then when something goes wrong, they spend way too long, like hours, days, sometimes weeks, just trying to hunt down what's causing the problems. So we saw like this is really a big issue. If serverless is going to gain adoption, this issue has to be solved first. So we kind of scrapped our original idea, and I'm happy to talk with any of you afterwards if you're curious about the original idea. I still think it's valid, but we decided that this is really important for us to solve this problem because 29 out of 30 said exactly the same thing. So we decided to build what is now IOPipe, and this is the only like pitchy slide you'll see. Sorry, but just to give you a background on what it is, so you can understand what we built, which is the pipeline. So we basically built this library that you add to your code, to your functions, and we instrument your code, and then IOPipe provides like the observability, monitoring, tracing, metrics, all of this kind of stuff, well suited for serverless applications. Because back then, all of the existing tools out there didn't work with Lambda. They all make an assumption that you have a agent that you can install on a VM or a container or a server somewhere, and it's like collecting the data and sending it off to their service. There's nowhere to install this in Lambda, so we had to take a different approach. So we ended up writing these libraries that wraps your Lambda function, and basically you just add the library. You like put IOPipe around the function handler, so it's a little bit hacky where we take over the handler, and then we're using that as a way to like go into your code base to look at performance traces of your calls. We're looking at like the underlying infrastructure, whatever we're able to see. We can look at like cold starts and memory CPU consumption and things of that nature. And now with Lambda layers, we don't even have to modify your code. So we recently just released like this installer, which you just type a command and it will just use the AWS SDK and add a layer. So it adds our library underneath your function, and then we just reconfigure the handler using the environment variables. And so that's the gist of like how we collect the data. The key part that I want to focus here on is that for every invocation, we do that instrumentation, and then that telemetry sends off to our service. That's the key part. Like traditionally, that would send to some local agent, and then it would aggregate that data, and then send the aggregates to the service. We don't have that luxury in serverless. So we realized like, well, let's just send it directly to us. But that created some challenges. So I'm going to talk about how we got through that. So some of the requirements were, we know we had to handle tons of events, like could be billions, could be beyond billions of events if we're collecting data on every single invocation. We can't do aggregation on write. We can't throw any data away. So it needs to be, first we realized it needs to be real time, because one of the things we found is that people expect these tools to be as fast as possible because they want to use it not only as like a operations tool, but as a developer tool. They want to have the visibility as they're coding, as they're iterating on the code, to see how did this change to my code affect the actual function and surrounding services. So we want it to be as real time as possible. And that to us is within like 3 seconds generally. So you're not waiting 2 minutes just to get an error or metrics back. We need to be able to handle very unpredictable spikes of traffic and data coming in, because we're running this as a SaaS and we don't know the traffic patterns of all of our customers. So we don't expect our customers to say, hey, we're going to get 1 billion invocations today. They don't tell us, they just suddenly send us tons of data. And that happened actually in our first week. Our second week, we built this MVP. We didn't even have a dashboard. We just had this library send us the data, and then we generated like a weekly report. And one of the beta users like put it into their production workload, and they had like 20 million users. So suddenly we had tons of data, like hundreds of millions of events per month coming our way. And we weren't expecting that. So we needed to make sure that it could handle that type of spike, that type of workload, because that's really what serverless is well suited for, especially in the early days. It needed to be low latency because, as I highlighted here, it basically needs to be able to send that data to us at the end of every invocation. That's still in the user's execution. So we can't take up all of that time, because execution time equals money in the world of serverless and Lambda. So you're charged for every 100 milliseconds. So if we take more than 100 milliseconds to send the data to our servers or our service, then that's going to cost our users extra money for every single invocation. So it needs to be really low latency. It needed to be startup budget friendly, because when we started, there were just 3 of us and we had like no money. We were just like, let's try this. So we needed to make sure we didn't have like tens of thousands of dollars to invest in infrastructure. And it needed to be resilient to failures. Again, there were 3 of us, so it needed to be very easy to operate. It needed to be very resilient so that we're not losing data if something goes wrong, especially in the early days when we're just figuring things out. Things can go wrong all the time. We need to make sure that the data pipeline is like the most stable and resilient portion of our infrastructure, so that when things do go wrong on either end of the data pipeline, we're not losing data for our users. And then we needed to make sure that it can scale to the volume that we needed, which was billions per day eventually, we anticipated. So I'll talk about how we put that together. So we were based on AWS because we're building these observability tools around Lambda users. We actually started on Google Cloud, and then we migrated to AWS primarily because of our pivot towards this. So we ended up building out, this is a bit of a high-level picture of our infrastructure. So we built this out. So the idea here is that you have Lambda functions on the left. These are the users' Lambda functions that are instrumented using our library. Those send the data to our collectors, which we run in every single AWS region. That's how we keep things low latency. But we'll focus just on a very simple use case of that in these slides. And if we have time, I can talk about that a little bit more. But basically, like, we use Elastic Beanstalk for the collectors. We tried to use Lambda originally, but the issues with using Lambda for the collectors is that it wasn't low latency. There could be cold start overheads. And also, at the time, it didn't work out like financially. Like, we would have to invoke a Lambda function for every user's Lambda invocation. So the math didn't really work out. So we chose Elastic Beanstalk because it was like low overhead, it has auto scaling. We don't have to worry about the servers. So it's sort of serverless, even though there's VMs. And it was the best option available in 2016. And it's worked well for us. We keep that piece as simple as possible. So that basically just takes the data and sticks it into a Kinesis stream, which is the next and main component of our serverless data pipeline. And it just returns like an HTTP accepted back to the user. So that part needs to be as fast as possible. And like from the Lambdas function to the HTTP accepted code is typically between like 5 to 20 milliseconds with this setup. So it's very fast, and it auto scales, so we can handle those spikes very, very quickly. And I'm going to talk about Kinesis through most of this, which is the bulk of the data pipeline. So we use Kinesis. I'll talk about that in a second. And then that basically we have Lambdas at the other side of that, which are consuming from Kinesis and doing things, putting it into various databases, and then we have an API and then a front end, and then you can see it via a dashboard. So that's kind of the high level. So Kinesis is really this. This is kind of the example diagram. I recommend checking out that link if you want to know about all the concepts of Kinesis. But basically, Kinesis is like a data stream. You can just throw data into it. It's basically like a ring buffer, so it has like a number that's like an iterator that basically keeps track of where you are in that buffer. So as you keep adding data in, you have a pointer that's going to like show you where you are in terms of like the consumers on the right-hand side, in this case Lambda. So those Lambdas are going to continually like grab the current point in data, the current point in the buffer where the data is, and then you can do things with that, process it, and then it's going to take that data off of the stream once the operation is complete. So Kinesis works really well because it handles things. It basically like lets you scale that quite huge. Like you can just keep adding shards to it to scale. There's theoretically no limits to that. There may be some limits that AWS has, but they are processing like tons of data with these things right now. It's also very cheap. It's basically serverless because there are no servers to manage for us. AWS takes care of that. And it works really, really well with Lambda. Lambda is very well suited for it. It's super easy to set up Lambda to consume data from Kinesis and process that data however you like. On the Lambda side, we are basically setting up this Lambda function to basically be a Kinesis trigger. So it's basically continually reading from Kinesis and grabbing a set of records, and it's processing those and then writing them into a database, and then it changes the iterator to the next point in time. So it's very easy to set that side up. It's very easy to set up the Kinesis side. It's just like 20 or 30 lines of CloudFormation if you do it that way. But then the trick gets into like, how do you set this up? Like, how do you configure it for the right scale? So it's important to know Kinesis does not auto scale. So you have to plan ahead, and you have to choose your shard size based on like how much throughput you intend to have. So basically, the shard is considered the base throughput unit of writes. So one shard can ingest up to 1 megabyte of data per second, or 1,000 records per second for writes. So it just depends on like the size of data or the amount of records that you have in the given period. You can kind of do that napkin math to figure out what that, how many shards you're going to need. An example is like 5,000 shards is going to stream up to 5 gigabytes per second, or 5 million records per second. And then the other side of this is the batch size. So the batch size is on the Lambda end, where the Lambdas are basically consuming the data off of Kinesis. So it's important to set that properly. So basically, you set that basically so you can retrieve up to 10 megabytes of data, or up to 10,000 records per call. So that just depends on like how much you think you can process within 1 second. So you want to be able to set this up so that the Lambda function can process it within a second. Because if the Lambda takes longer than that, then you're going to basically get these exceptions thrown, and you're kind of not an optimal setting for this, basically. So examples like one shard has a read rate of 2 megabytes per second. So this can kind of help you figure out like what you want to do here. So 2,000 documents can be processed in a second. 1,000 documents can be processed. Sorry, 2,000 requests or documents can be requested once per second out of 2 lambdas, and then 1,000 can be 1 lambda, or one document takes 1 second. That takes 1 lambda. So it just depends on what type of data you're going to have, how big that data is, and then how many records you have. So you can kind of do that math, figure out what your batch size and shard size should be, and away you go. And it should just work. You can always change these things on the fly, but there are some gotchas here. So one of the gotchas is that Kinesis stores this data for 24 hours. They do have an option to change that to 7 days, which is a good idea if you're very paranoid about data loss. It costs more to do it, but it's not terrible. And it gives you a lot more like assurance as to like if something goes wrong, like for example on the Lambda side, the records coming in are still going to keep coming into Kinesis. But if the Lambdas for some reason stop, like maybe you pushed some new code updates and it's not getting the data properly, that Kinesis stream is going to basically fill up with data. And what's going to happen is like the iterator age is going to keep increasing, and the buffer is filling. And it's going to stay in there for 24 hours, which is great. But if it takes you longer than 24 hours to fix whatever issue you have, you're going to start losing data. So you can change that to 7 days, and now you have 7 days to kind of fix the issue, depending on your use case. But that kind of gives a little bit of assurance. It made us feel a lot more comfortable in the very beginning when we were not sure if this is going to work for us. So we set it at 7 days, and we felt a lot better. Scaling Kinesis is a little interesting. So as I said, it doesn't automatically scale, and it's not instant either. So you have to kind of plan ahead. You have to be able to over provision in case you do expect to have like huge spikes of activity coming in. Up, down takes minutes, and you can basically only scale it a couple times a day. And each time you scale it, you cannot go more than double what the shard count is. So you have like a limit to the number of times you can scale it in a 24-hour period, and then you can only double it or less each time you do that. So you have to kind of plan ahead, especially if you have like big anticipated data coming in. One example for us is like we have some customers that are in the retail space, and Black Friday, Cyber Monday coming up, they expect a huge amount of volume. So we kind of work with them, try to figure out what their anticipated volume is going to be. We massively over provision days in advance so that we're ready for that. And like the last Black Friday, Cyber Monday, there were no issues with this, but it's something to know. It's not something that just automatically happens for you, unfortunately. And there are limits to the account and region level in Lambda, but apparently these are pretty easy things to change. There's a form you can fill out in AWS to get those things changed. So if you do run into some limits that they have set, they're very arbitrary limits, and they're not technical limits. So it's pretty easy to get that stuff changed if you need to go beyond what the defaults are. So how much did this cost us to put together? So one thing I forgot to mention is so we started with Elastic Beanstalk, which is basically EC2 instances that's being managed by AWS. It's doing auto scaling. Fargate is a newer service that came out, which is basically like a serverless container service. And we're now like experimenting with Fargate in some of our regions because it's while Elastic Beanstalk works very well for our collectors, some of the issues we have are that the scaling is a little bit slow. So if we have a huge spike of workloads, they have to spin up EC2 instances, and that can take like half a minute or something. Whereas Fargate is using containers, and the spin up time is like single-digit seconds in most cases. So we're able to scale up and down really fast with Fargate, which is primarily why we like that. And it still has the same performance as the EC2 instances that are underneath Elastic Beanstalk. So this calculation is basically using Fargate because this is kind of what we're moving towards. So you can see Kinesis basically is charging for the shard hours. So depending on how many shards you have times number of hours in the month, and then they're also looking at like how many put records you have. So I just did a very basic calculation of 1 billion records. Fargate is kind of the same thing. You pay for like the compute hours of that. So assuming like we need to always ingest data, let's keep it up. We keep it up all the time. So it doesn't spin down, because if it spins down to 0, that startup cost is going to have like it's too low performance to like spin down to 0. So that costs like $36 roughly, depending on how many CPUs and memory you need in that thing. And then the Lambda side, for 1 billion records, 1 billion records coming into Kinesis is going to have a minimum of 1 million Lambda invocations, and that costs about $2.70. Maybe it's free if you're in the free tier still. So you can, and the free tier gives you 1 million invocations per month for free forever. So it's very cheap. It's $63. That's one region though. We started with one region, and now we've expanded to all regions. So we have like a replica of this setup in every single region. But even then, we're supporting like globally all of the AWS regions for a very small amount of money per month. Our actual setup is more than this because we have a lot more shards now. But this is pretty cheap compared to what it would have been to process 1 billion requests. Not just like 7 years ago. This would have been a lot harder. So monitoring the pipeline, since this is a really critical part of our infrastructure, like this is the one piece that we really can't let go down, because that means like data's not coming in or data's getting lost. The other side of that, the Lambda side going into the databases, is less critical. It's still critical, but if that goes down for any reason, the data is not lost. It's just slower to get into our system. So that's a little bit more acceptable. But if Kinesis were to go down, or we had some issue with the collector side, that's a really big deal for us. So we set alerts on the iterator age. So if the iterator age starts climbing, you're in trouble because the data is not getting pulled out of Kinesis. So that means like whatever you're doing with that data, in our case, like it's going into our dashboard, it's going into alerting system that we have built. It means all of that data is delayed. So we get PagerDuty alerts the second that iterator age goes up. And you can set that in CloudWatch. The other thing we look at is invocation spikes or drops on the Lambda function that's consuming data off of Kinesis. So typically that Lambda function is going to have a pretty flat rate of running. So based on how many shards you have. It doesn't really change because the Lambdas are tied to like how many shards you have. So unless you're adding or removing shards, that is going to be very flat for the most part. So you can set alerts based on like no more than X invocations per minute or no less than X invocations per minute. And then you'll get alerted whenever it goes above or below that threshold. And that's saved us a few times where there's an issue with Lambda in some regions. Like a few weeks ago, US West 2 had a total outage of Lambda for like a couple hours. And our alarms started going off because that Lambda function suddenly dropped in US West 2. And we got alerted of that, and we quickly knew within like seconds something was going on. Unfortunately, we had to just wait for AWS to fix it. But other regions were working, so that was good. And for us, we're also looking at like failed writes to the database. So we instrument on the Lambda side as well what's coming into the Lambda function from Kinesis and what's going out. So we can look at like if any of the writes to the database are failing, if there's any timeouts or errors in those functions as well, the Lambda function. And then we're also doing like canaries where we send test data through the pipeline, and then we're looking to make sure that that's actually coming out continuously. So if that ever stops, we know somewhere in that pipeline there's a problem. So that's how we set things up. We also use our own product, IOPipe, to observe IOPipe. It's a little weird, but for parts of our system, we're able to do this. And basically what we're doing is like on the top left here, you can see those are the Lambda functions reading from the Kinesis stream. So you can see it's pretty flat, especially that top one that's kind of maxed out. So that typically doesn't drop. If it does, that's a problem. And we're instrumenting those Lambda functions that we can see like how many records are coming from Kinesis, how many were attempted to write into the database, how many were skipped for whatever reason or failed. And we have alerts set up on all of these things so that we know when something goes wrong. When there are timeouts, which happens like pretty frequently actually, there's timeouts like every day. Like there's going to be multiple timeouts. Like for example, in this screenshot here, there's like 7.6 million Lambda invocations. That's a 24-hour period. Like I took that screenshot yesterday. Those functions are just running like all the time. Sometimes there's going to be timeouts because Lambda functions are relying on other services. In our case, it's a little bit more complicated than the diagram I showed. We basically read from a Kinesis stream, process the data, that writes into a few different databases, and then a subset of that data is then put into a global Kinesis stream that we have like centralized. And then that data is being processed for other types of data in less real-time nature. So we're kind of like aggregating all of the data together from all of the regions and then putting that into another database. So sometimes that write into that Kinesis stream fails for whatever reason. It times out. So you can see an example here in the screenshot here, like there's a timeout. We have tracing set up so we can see all of the calls, and the bottom call there, you can see this Kinesis, it's hard to see, but Kinesis put records is that bottom one, and it has like no end trace. So it means it started, but it never stopped. Some final thoughts here, I'll go quick. This works really well for us. We've been processing billions of events per month and very spiky. Sometimes we have billions per day. And Kinesis has not really let us down at all. The Lambda side has been a little bit iffy here and there, but the data has never been lost, which is really key. It's very cheap, and it's very easy to manage. So kind of graded these sections here. You can see basically it hits the real time really well. It handles unpredictable spikes across many regions pretty well. It's pretty low latent, and it marks all of the marks for us quite well. Some of the issues we ran into are around there being no back pressure built in. So if your database can't handle all the data coming in, that's a problem that you have to deal with somewhere. Kinesis does not do that for you. So yeah, that's pretty much it. I don't think we have time for questions, but come find me afterwards. I also have some stickers if you want to grab some stickers. I'm happy to chat with you. Thanks a lot.